Hello everyone, welcome on this e-learning platform of Apex Institute of Physics. We are learning electrostatics, and in that some important electric field formulas because of some charge distributions. Here we are going to discuss about the electric field due to a uniformly charged semi-ring. So there is a picture in which half of the ring has been shown and it's uniformly charged. So let's say charge density is lambda and its radius has been shown as r. We are interested to find out the field because of the semi-ring charge distribution at the center location. So the focus is at the center of the curvature, and we will be finding the total field at this point. Since it's continuous charge distribution, so we will be taking a differential element, finding the field, and then integrating it to find the final field, right? So let's say this is the reference line, positive x direction. From here we are measuring an angle theta, and after going that angle theta, we are considering very small element of having angular gap as d theta, and this length on the semi-ring is going to be equal to r d theta. We know r is the radius, d theta is the angle, so arc length is radius into the angle. Now on this length of this semi-ring, the total charge that will exist, if we call it as a dq, so that total charge dq is going to be lambda into the length, and the length is r d theta. So this is dq. Because of this small charge element, we need to find the field at this point, which is the center of curvature. We know because of any point charge, the field at a distance is in this direction. So field is going to be, let's say this is dE, and which is going to be away from joining that line. Now since as this charge, this differential charge location changes, the direction of D will change. So to get the total field, we must integrate the differential field vector. And to do the same thing, we can have components of this and then sum them numerically, right? So we will make the two component of this field, one along the direction of x, which is horizontal direction we can call, another vertical direction. Now if this angle was theta, we are sure that this angle is going to be theta, so this component will become dE cos theta, and this component, vertical component, will become dE sin theta. Now when we move this differential element, D will change its direction, but all the D's will have a component, one horizontally, another vertically. So the total field along the x direction will be equal to Ex, which can be written as integration dE cos theta, and the total field in the y direction will be integration dE sin theta, which will be Ey. So let's do one by one. So dE cos theta, we can logically handle this expression because this is symmetrical from theta equal to 0 to theta equal to 180 degree, and we will find half of the elements will have a field in the negative x direction, second half of the element will have a field in the positive x direction. So the total sum of this dE cos theta will be 0. So this must come out to be 0. We can check it mathematically as well. We know this dE will be because of a point charge, so that's going to be k dq divided by r square into cos theta. Now substituting the value of dq, which we have already written there, so this will become integration k lambda r cos theta d theta divided by r square. Now as far as the limits are concerned, this limit will be running from 0 value to 180 degree, or we can say pi radian. Now performing this integration, we will find this Ex will turn out to be this k lambda upon r will be outside, and this cos theta will be integrated into sin theta, and the limit will be running from 0 to pi. We know when we place this limit, we will get our answer back. So this will become k lambda upon r. In the bracket we will get sine pi minus sine 0. We know sine pi is 0, sine 0 is 0, so entire number will come out to be 0. So we'll find the x component of field is 0, which otherwise can be indicated by using the common sense or components theoretically. Now the important aspect is to find this Ey components. That's going to be the total value. So Ey is going to be integration of dE sine theta. We can say this integration will be very similar to the above one. That means we need to place dE value, which is going to be k. dq can be written as lambda r d theta divided by r square, and sine theta, so we can write it as a sine theta d theta. Instead of cos theta, which was here, we have simply replaced as a sine theta. Now we can further move ahead and we can say this is going to be k lambda upon r outside, and then in the integration we will find sine theta d theta. Now sine theta d theta, this will have a limit running from 0 to pi. We know sine theta integration will become minus cos theta, so k lambda upon r. In the bracket we will get minus cos theta, and limit will be running from 0 to pi. By solving this, we will find the value of Ey, the component in the vertical direction, which is the only component we are having, k lambda upon r, and then we will putting the values. So since this is a minus sign, we can swap the limits. So ultimately it will turn to cos 0 minus cos pi. We know cos 0 is 1, so this becomes k lambda upon r, and cos 0 is 1, and cos pi is minus 1, so minus of minus 1. This minus and this minus will become plus, so 1 plus 1 becomes twice. So answer comes out to be 2k lambda upon r. Finally, what we have achieved or proved or found out here is this. There are two components of field. One is Ex, which is equal to 0. Another is Ey, which is equal to 2k lambda upon r. So if we square and under root or whatever, we say that this field is 0, so Ey is going to the total field. That means because of a semicircular ring, the field at the center is in the vertical direction in this particular case, and this value is 2k lambda upon r, where r is the radius, lambda is the charge density, k is 1 upon 4 pi epsilon naught. So that's also one of the important result we can remember. One more thing, we can have a relation here. We have already talked about the field because of infinite linear charge distribution, and in that case the total field came out to be 2k lambda upon r, where r is the distance from the wire. So that means we can say the field due to a semicircular ring is similar as the field due to infinite wire, which is a linear charge density. So this is a similar formula that we have got here. Let me further illustrate the relation between the linear charge distribution and this semi-ring. We have talked about this infinite linear charge distribution. The field at a distance particular from this line over is in this direction, and its value is E is equal to twice k lambda upon r. In a very similar fashion, we have also proved that the field, because of the semi-ring at the center point, is in this direction, and that field is 2k lambda upon r. Now we see the fields, they have the same magnitude if the distance, this is also equal to radius of the ring. Now that means these two charge distributions are identical or similar as far as the field at this point is concerned. That means if the charge distribution is in the form of line running from infinite to infinite, then the field at this point will be the same as if the charge is distributed on this semicircular part of the ring. which further can be correlated as if we take this infinite location point and we bend this infinite location point and this turn all this by 90 degree and bring here to form this half part of the ring, and similarly doing this infinite, bending it by 90 degree, we can get this. That means bending of this in uniformly linear charge may create this kind of picture. So this kind of charge distribution will have no effect in the total field at this location. So as far as the electric field is concerned, we can replace this charge distribution by this whenever it is needed, and we can also replace this by this whenever it is needed. Now this may help us to find out the field because of various charge distributions, and sometimes it will be very easy for us to relate these two things. We will see that by an example. After learning about the electric field because of semi-ring, let's talk about the electric field due to quarter of a uniformly charged ring. So this is a quarter of the uniformly charged ring. Let's say charge density is lambda, which is uniform, and its radius is r. Because of this, we are interested in find the field at the central location. Now we can say at the central location, by symmetry, the field will be whatever the field is, that field is going to be along the direction which is symmetrical direction, and the symmetrical direction will be the angle bisector, and which could be written as this. The net field must be in this direction, unless that field is E. We can also claim as for this quarter of the ring, the field is in this direction. If we consider this dotted quarter of the ring, the field must be along the angle bisector again. And if we join this angle bisector here, we will find the field is going to be directed along that angle bisector. One thing is going to be sure, as this quarter of the ring is the same, this is the quarter of the ring, so magnitude of both the fields are going to be equal, that's E. Hence if we join these two segments together, so this will form the semi-ring, and the semi-ring will have a field because of the resultant of these two fields. The resultant of these two fields are going to be definitely in this direction. We already know because of the semi-ring field is in that direction, and the total field comes out to be 2k lambda upon r. So we can use the vector here. We can find the resultant of this vector as well as this vector field must be this vector field. Now since this is a quarter of this, we can find out this angle is going to be 45 degree. So we will find this angle is 45 degree. That will lead to this angle is going to be 45, this is going to be 45, this is going to be 45. Point is, these two vectors E will be at 90 degree each other. So the resultant of the two vectors which are at 90 degree, we know that's going to be square root of E square plus E square. So this magnitude must be equal to the total field that we have calculated, which is 2k lambda upon r. Now from here we can say this is going to be equal to E, which is going to come out under root 2 as a factor, is going to be twice k lambda upon r. After simplification, we can claim from here the field because of this quarter of the ring is going to be root 2 times k lambda upon r. So that's going to be the total field because of quarter of a ring, and the direction we can think of, the direction of this field is going to be equal to angle bisector, which means we can make the two components of field because of a quarter of the ring, one along the direction of x, another along the direction of y. So if this field was total field, so the total field, this field E, because of this quarter of the ring, have two components, one along this direction, another along this direction, and the resultant field came out to be this. So this E is in this direction. That x component, if we make the x component is this 45 degree, we can call it as a k lambda upon r, and this component is also going to be k lambda upon r. So again the point is the quarter of the ring will have a two component, one on the horizontal direction, another on the vertical direction, to give this direction bisector field, right? And both components are going to be k lambda upon r, k lambda upon r. So either we can remember in this form and angle bisector, or we can remember in these two components form. Both are going to be equally correct. Now we can further go ahead and relate the semi linear charge distribution, the quadrant of the ring, as we did for this infinite charge distribution for the semi ring. Now we have already calculated earlier the field because of this semi-infinite charge distribution came out to be with the two component. One was in the perpendicular direction, so at this r distance we had this component and we had this component of field. And if you remember the previous lectures, you will find this field came out to having a component k lambda upon r and k lambda upon r, the two components. So the resultant field used to be at the angle bisector as k lambda upon r under root 2. Exactly same formula we have just proved for the quadrant of the ring. At the center point we got two components, one in this direction, another in this direction. This component is we have just proved is k lambda upon r. This component is also k lambda upon r. So the total field is along the angle bisector. Now you see this these two charge distributions are exactly identical as far as the field at a distance r is concerned. So point is, whenever we need, we can replace this semi-infinite by quarter of this and infinite by the semicircular ring. Right, so that means this analogy is not only true for this part but also is true for this part. Based on this, let's see one example. So here is example to use those correlations or results. The question says find electric field at point O is here in the given charge distribution. So here we have been given 3/4 of a ring and this semi-infinite linear charge. We can convert this 3/4 of the ring as a semi-ring and one of the quarter. So we know the field because of the semi-ring, we can find here at 2 point. We know the field because of the quarter of the ring, we can find here. We know the field because of semi-infinite linear charge, we can find here field at that point O. Then we can sum up all the three segments to find the total field at the point O. That can be easily done. But the correlation that we have just understood, if we use that thing, we can simplify this very quickly. We know this semi-infinite linear charge distribution will have a same effect as quarter of a ring. So if this infinite point end is bended by 90 degrees, so that will become quarter of the ring, and that quarter of the ring will appear some sort of this. This will be almost going to behave like this. Now if we replace this infinite by this thing, then we will say the effect of this semi-infinite linear charge will be same as that of this quarter of the ring, and vice versa. So that means instead of finding the original configuration, we can find out the field because of this new configuration, forgetting this. If we are forgetting this and we are considering this as a part of the this charge distribution, then we can say this is a complete circular loop. And then we know the field at the center of the complete circular loop or ring is 0. That means we can claim at O field will become equal to 0. Now this is quick answer by using this charge distribution, converting the charge distribution from linear to circular arc. This kind of questions we can handle using this thing. So this is our final answer. Also this was field because of quarter of the ring and semi-ring and their applications. Please follow it properly, make the notes, they are important for exam point of view. Thank you.